So the next thing that we didn't get around to doing, we talked about the dry gas material balance, and we didn't really discuss the effect or whether you could use those dry gas material balances for gas condensate. So we're going to talk about that topic now. And so we're talking about, if you look at any reservoir engineering textbook, Dake, Craft and Hawkins, what I grew up with, Amix, Bass and Whiting, probably any of them, you're going to find many different equations of state or different material balance equations written like this. The simplest being what we looked at yesterday. The so-called straight line. Dry gas material balance. This is evaluated at, of course, reservoir temperature and average volumetric reservoir pressure. This is, of course, at initial reservoir conditions. GP is the cumulative gas produced, and G is the initial gas in place. Okay. This equation is based on two assumptions. Assumption one is that the hydrocarbon pore volume, which is just the pore volume of the reservoir times the initial water saturation, right? That this never changes. So the volume containing gas, that's basically the volume of the reservoir containing gas, remains constant. So the pore volume doesn't change because of rock compressibility. The water doesn't expand because of compressibility. You don't get water encroachment. It's the idealized. It's like a PVT cell. So that's the one assumption, the main assumption for this. And the second assumption is that you have only gas phase. In the reservoir. And thirdly, that you only have a surface gas product. That is no surface condensate. Okay. Now, this equation, or likewise, if we use with the pod aquifer version of this, remember yesterday I talked about that, 1 minus CE. This is just one of very many forms of the equation. This equation changes this because here the hydrocarbon pore volume changing. Okay. But 2 and 3 are the same assumptions. Okay? That there's only gas in the reservoir, there's no retrograde condensate or reservoir condensate, and there's only surface gas product being produced. Okay? So if I ask the question, does this first equation or the second equation apply to what we call in the industry, basically we have, when we look at reservoir fluid types in petroleum reservoirs, we have dry gas, right? And we have wet gas. We have gas condensate. And then we have different types of oils. So dry gas has the same two features that we're talking about here. There's only gas phase in the reservoir, and there's only a surface gas product, right? So 1, check mark, and 2, check mark. But for the wet gas, 1 is a check mark because you never see liquid in the reservoir. In a wet gas, basically these two both have reservoir temperature greater than what's called the cricondon therm. Okay. Remember when we look at our phase diagram, looks something like that. This cricondotherm is this rightmost temperature, and at all temperatures above that, you only have single phase fluid. We're going to call it gas, but it's single phase. So out here, it's single phase. And if this was a critical point, then if the reservoir temperature was between here and here, that would be a gas condensate, right? We should have introduced that definition on Monday, but we didn't. So basically the definition of a gas condensate is that the reservoir temperature is between the cricondotherm, which is this temperature here, and the critical temperature, somewhere between there. That's a gas condensate. So the wet gas and the dry gas both are at a temperature greater than cricondotherm, but the wet gas, what happens there, let's say that this is the initial pressure and temperature. If the phase diagram looks like this for that wet gas, the point is that if the standard condition, let's say it's here, is inside the two-phase region, right? So by hook or by crook, it makes it from initial reservoir condition here down to the surface conditions, which is a separator at stock tank conditions, and that's inside the two-phase region. So we're going to condense out liquid at the surface. That's what the wet comes from. You actually you produce condensate. It'll look like water probably. Okay. A dry gas would have to have a phase diagram that looks something like this. It might look like this. Okay, that would be a dry gas. So that when you reach the standard conditions, you're not in the two-phase envelope. So it's still gas at those conditions. Okay. So if you have a wet gas, how do you modify or use these equations here? Can you use them? And if so, how do you do that? So I'd like you all to suggest something. So if we have a wet gas, this is being violated here, and it's being violated here for wet gas. So how to correct the so-called dry gas material balance for a wet gas? Why are we going to talk about that? Well, we're going to talk about that because we need to do the same thing for gas condensates. Okay? Because gas condensates produce two products at the surface. So any suggestions on how to do the correction here? Anybody want to come in with a suggestion from outside?
Maybe to use a GOR.
To use a what?
Gas oil ratio.
Okay, we're going to use the GOR. That's correct. But the question is how to use it. Okay. Okay. So what we're using here is average reservoir pressure, Z factor at reservoir pressure. These are the three variables that we have in the material balance, right? The pressure, the Z factor, cumulative gas produced, and the initial gas in place. So what we're going to have to do is that we're going to have to change these two here such that the standard cubic feet we're talking about in both cases, or standard cubic meters if you're communists. That's a joke from a guy from Oklahoma. You know, if you don't use units like us, then you're against us, right? So if you're using the GP and the G here, then the standard cubic feet or the standard cubic meters, they have to be what we termed on Monday as wet gas volumes, fake gas volumes. Okay? They have to be wet gas volumes. Okay? So in your daily production history, you've got basically QG, Q oil, you're not getting very much, so you might be getting, 12 million, standard cubic feet per here, and you might be getting 6 stock tank barrels here. It's not very much. This is 0.6, about 0.5 barrels per million, right? It's not very much, but 6 barrels is 6 barrels. You don't throw it away. So this is our production history. So this is day 1, 2, 3, kind of like that. And so what you have to do is that you have to convert this gas here, which we're going to call like that and that. We're going to have to convert those into a fake wet gas volume. And that fake wet gas volume is, I think we came up with the equation. It's C, it's QG, which is dry. This is the same as QG dry. These are the same thing. So it's the QG dry plus the COG term, I think, times Q stock tank barrels. I'm pretty sure that's right. This term here has units standard cubic feet per stock tank barrel. So it's the fake equivalent surface gas. If you could turn these 6 stock tank barrels of oil and vaporize it into a gas at standard conditions, then the number here, that number is typically around 500 to 700. So somewhere in that range. Okay? You get that many extra standard cubic feet. So we have that equation. And I think that equation was, COG equation was 7.13. Pretty sure. Okay? So that's all you have to do, but you have to do it. It's you know, I don't know what you call it. You should do it. Huh?
7.13 in the monograph.
In the monograph. Yeah. Okay. So that's the correction. And that same correction has to be done for gas condensates. Okay? Because the problem with gas condensates is that this combination here, this only gas in the reservoir, this gas condensate violates that, right? And so we have to do something extra to make these gas material balance, these conventional gas, dry gas material balance equations work for a gas condensate. So the first thing we have to do is we have to convert, you know, sales gas and stock tank oil into a fake wet gas. And we have to do one more thing. So we're going to talk about that.
So for wet gas, there is no need to change the Z factor.
No, the Z factor is single phase gas in the reservoir all the time. We're out beyond the Cricondensate. So you use the regular Z factor for the wet gas or dry gas, because in the reservoir it's all single phase gas, and that's what these assumptions rely on. Okay, so now basically how to correct the dry gas material balances for gas condensates. So one is you have to convert GP to a fake wet gas, same as we do now. The COG could theoretically change a little bit over time. Normally it's neglected, but if it did change over time, then you would have to do it. You would have to do it this way. You'd have to do GPD plus the summation of QO COG, which is now varying with time. Okay. Times delta T, whatever, daily or monthly or whatever. So you'd have to integrate that into there. But normally we just assume this is constant. For gas condensates, it's more likely it'll vary, but just so you're aware of that. The second is that we have to take into account the fact that we have in the hydrocarbons pore volume, which could be changing because of water influx. So that second equation up here, you know, that's okay. So this equation, the hydrocarbon pore volume is changing, that's fine. But what the hydrocarbon splits, it's got basically a volume of gas in the reservoir and a volume of condensate in the reservoir. So we need to correct for that. Okay. And to do that, we use what's called we have to use, and it's provided by the laboratory from the CVD test, the two-phase Z-factor. And we use those at all reservoir pressures less than the dew point pressure, the initial dew point pressure. Okay? So that's the requirement. And if you haven't seen the two-phase Z-factor in the PVT report, then I'll show you what it looks like. But if you're going to use MBOW or some kind of Excel gas spreadsheet like we were using yesterday, you have to bring in this two-phase Z-factor at these pressures below the dew point from the lab into the software. So if we look at Z-factor, and I'll put maybe 1 here. So this is the dew point. So I'm going to draw in red so I'm going to draw this. Might look something like that. Out to maybe initial reservoir pressure. And then the PVT lab will so these are single phase gas Z factors from the constant composition expansion test. Okay. And then we're going to have true gas phase Z factors from the CVD. Okay. And they're going to look like this. Okay. They will be approaching 1 at low pressures. But what's going on with these is that for the CCE, the gas composition here is constant. Okay? Whereas below the dew point, the gas composition from the CVD is changing with pressure. So the change of Z factor with pressure has got 2 effects. It's got the change in pressure, which gives a change in Z, but it also has a change in composition. So it's got 2 effects causing it to look like this. Okay? And it should kind of be extrapolating towards 1. And then they're going to give us this strange thing called two-phase Z factor, and it'll be only below the dew point, and it's going to look something like this. It kind of looks like it's got this funky non-monotonic shape. Now this is not going to 0, this is probably going to 0.5. It could go down to 0 for a really rich condensate, but it's got a non-monotonic and it's not pointing towards 1. Okay, so that's our two-phase Z factor. And it's not physical. It's not a physical Z factor. Although I think there's a couple of papers in the literature that suggest it's physical, and they kind of tell you how to calculate, but it's not physical. Okay, so that's.
But if we have a regular CVD data and they don't report the two-phase Z factor, can we calculate that?
Yeah. So it says it's from the CVD test. if they don't happen to give it to you, then you'll find in the monograph from equation 7, equation 6, in chapter 6. You'll find it faster than I do.
6.38.
Huh?
6.38.
6.38. It gives you the equation. Okay. I'm just going to tell you real quick how they come up with the two-phase Z factor, even though the equation's given there. I'll just kind of tell you where it comes from, so it's not mystical. So in the CVD test, as a function of pressure, first pressure is the dew point, and then I'm going to call that P1, P2, P3, P4. Okay. The one data they give is something they call moles produced over moles at the dew point initially. Okay? So that's moles removed or produced. Cumulative. And ND is the moles initial at the dew point. What you start with in this experiment. Okay? Now this is actually equivalent to GP fake wet gas over initial wet gas in place at the dew point. Okay. So they give you that. And then what they say is that we're going to force that data we're going to plot GP wet over G wet. And this is because, you know, starting at the dew point. 100% 0. And what they're going to do is that they're going to plot P over Z. And the first point here is the actual dew point divided by the Z factor of gas at the dew point. So that's the first point. But what they're going to do is that they're going to force this material balance. They're going to violate all of the assumptions because it's not going to be a straight line. Because the hydrocarbon pore volume okay? They're going to force that line to work. So we basically go in with this, and this is really nothing more than the recovery factor of this fake wet gas. Okay, so this recovery factor, of course, that's 0 at the initial dew point. And we get the recovery factor 1. This is basically our recovery factor, what I'm calling recovery factor. They go in with that 1, and that value is here. So they go into this line at that value here, and they get a value of P over Z from this straight line. Okay? And then they get the second one from the second depletion. They go in, they get that point there, and they there. So I'm gonna have to move this down. So what they do is that they read from the straight line the P over Z from the straight line. These values here. Okay. So that's P over Z 1, P over Z 2, P over Z 3. Okay. And then they know the pressure at each stage, so then they calculate Z factor 2, two-phase Z factor, as the actual pressure in the CVD test over this P over Z straight line. So whatever Z they need to put it on the straight line, they get it. All right.
So two-phase Z factor is only used to correct the material balance, the dry gas material balance for the gas condensate. There is no other.
It's only used when gas condensate applies a dry gas material balance equation. That's what I think IMBAL is doing. You know, you have all versions of it. You know, with full aquifer support, you have the pot aquifer model. Probably you have, you know, the straight line, the most simple of all. So if you want to use any of the conventional dry gas material balances, you can do that if you impose this two-phase Z factor below the dew point. You'll never use it for anything else, any other calculation. Okay. So let's just say that we actually took production data and did everything what we were supposed to do. So this is actual field data. So we kind of have that. We're plotting P, R over Z, and the Z, of course, this is the dew point. Down below here, we're using Z is equal to the two-phase Z factor. And above here, we're using the actual Z is equal to the actual gas Z factor. Okay? So we start getting production data. And let's say it's an ideal reservoir. It's a straight line material balance, or it could be correct, whatever. So let's just say that we start getting these data. High permeability, so you expect a single reservoir flow unit. You got some scatter, make it look real. Of course, Dake, he once had a luncheon lecture. What was the name? What was the title of that? It was like something like why never to use the gas material balance, or something like the death of the gas material balance. Okay, and his argument was that you never see real data that follows this. Okay, that's not true, because some of the really big gas reservoirs, high perm single reservoir flow unit like the Hewitt, first UK big, okay, follow just like this. But there are many that don't. So if you've got something flowing like this, so what, and you extrapolate here, what I want to just discuss here is that if you extrapolate here, which is the main purpose of this, you get this initial gas in place. Okay? But let's say in this region here, we're producing with approximately 200 stock tank barrels per million standard cubic feet of gas. Okay? Well, the extrapolated initial gas in place is not related to the actual sellable produced gas. It's this fake gas. It's the face gas.
On
Okay.
the x-axis, we plot the GPW.
Huh? That's right, because what we're plotting here is GP fake wet gas. You know, there's very few things that we can, I think, thank Trump for. You know, maybe you're politically disagree, but the term fake took on a meaning, okay? And I can use it like before I would talk about wet gas volumes. And people would think, you know, it's a wet gas. It's a gas that's wet. It's not a wet gas. It's a fake, fictitious, not real gas. And then you just say fake gas, then they know that this fake wet gas is not something real. So what you want to do here is you have to take this number here and decompose it into the two products, which is dry gas, okay, which is our dry gas initial in place, and our initial condensate in place. Initial condensate in place and our initial dry gas in place, okay? So you have to decompose that, again, using the 200 barrels per million and the COG, okay? GW is equal to GD plus in COG, initial. So you basically get this from the material balance, you got that from your PVT, and then the 200 barrels per million tells you how to see. So basically with the initial producing and COG, we can decompose it into these two numbers. I'm not telling you exactly how to do it here, but you can do it. So that's the point, is that what you get is a fake wet gas in place number. You have to decompose that into the actual sellable gas in place and the condensate in place. Okay. Now, I would have hoped, because I know myself, I couldn't figure out why does this have this non-physical behavior? You know, what's the reason for that? It's totally nonsensical the way that's turning. And the reason for that is that if your last stage here was atmospheric, for example, then the recovery here is less than 100% because you've got condensate left in the cell, right? You may only produce, this last number might be a number between 85 and 98%. But what the lab is doing, what we're doing here is that we're forcing this to go to 100%. We're forcing it to extrapolate to something it will never reach unless we divide by some crazy two-phase Z factor. That's why you're getting these crazy numbers. So that's the reason why it turns crazy. Here. Actually goes down towards infinity. I mean, I'm not even sure. I've never taken from the PVT package and calculated two-phase Z factor. If you deplete the CVD and the EOS model down to very low pressures, 1 atmosphere, it's going to go towards 0. That's not very small numbers. Okay, so that's everything I wanted to cover, unless you have questions on how to correct gas material balance. Okay. All right.
I'm sorry, Curtis, I have a question regarding the POZ plot you just built up. But for the field, when we have lots of wells, how can we build a POZ plot? Because usually I think we are building it for each well separately until it reach some limit, I guess.
Yeah, so that's really a question that's more general than not for gas condensates, but for gas reservoirs as well. So basically, you know, the question is related to the gas material balance application to individual wells, right? Versus to a field, okay? And so let's say that the field if the field has only 1 reservoir flow unit, okay? So all the wells have their straws into the same common source of supply, okay? So So you can use individual well material balance only if basically the rate of the well to the rate of the field remains constant. Okay? Because if you look at the early literature, I think the book by Matthews and Russell, the first monograph, I think, on well testing, it was maybe the very first monograph. You know, basically you can show that for pseudo-steady state, or what they now call boundary dominated or pseudo-steady state, if this applies, then that infers that the hydrocarbon pore volume of that well over the hydrocarbon pore volume of the entire field, reservoir flow unit, I would say, remains constant. And that means that the individual well hydrocarbon pore volume is remaining constant. You're taking the same contribution from the field volume at all times. But this is seldom the case. But if it was, if you pre-drilled all your wells, and maybe Hewitt was like that. They pre-drilled all the wells. They started producing from all the wells, and they more or less all the wells. One well that's a dog well may produce only 3% of the total volume, and the best well may produce 13%. But as long as nothing happens to the integrity of those wells, that it'll be 3% and 13% for the whole life. Then you could have individual well material balances, and you would be getting the G that you extrapolate to would be the well initial gas in place. But that's not very common. So you can only use it there. In general, the gas material balance should be used for, so in general, the gas material balance, or really any material balance, applies only to a single, what I call reservoir flow unit. It's bounded, it's not connected to other reservoir flow units. It only applies to that one bounded reservoir flow unit, okay? And so what you would have to do is that you would have to say, you have to have your well list that's producing from that reservoir flow unit. Well, 1, 3, 8, 12, and 16. And then you would take and sum all of the cumes at a given time, okay? And so your cumes and your average pressure would be for the collective group of wells, okay? So that would be something like this. So it would be GP would be the sum for the wells in the reservoir flow unit. Okay. And the average reservoir pressure that you're dividing by Z here. Okay, so let's say that well 1 is in blue and well is 3 and pink. I won't do them all. 8. So you can take and do something like this. That's the way it should look. So you have different shut-in times to get different average pressures, but if they're truly in a common reservoir flow unit and everything is behaving as it should, this is the way it should be done.
But if we have several reservoir flow units, then it's not that easy, I guess.
If you have more than one reservoir flow unit and the different wells are connected to the different flow units, in other words, if a single well is connected to 2 reservoir flow units, you have a problem because you don't know how much this month's production is coming from reservoir flow unit 1 and reservoir flow unit 2.
But still we can use a PLT for separating production.
Yeah, I mean, if you have ways to come up with those separation, but you have to do it. Because what we talked about yesterday, the layered no crossflow behavior is exactly what you expect. Reservoir flow unit 1 will not deplete at the same rate as reservoir flow unit 2 unless you just are lucky. And you're usually not lucky. So you need that differentiation, And the other problem is that you need dedicated wells to get the average pressure for the individual reservoir flow units. That would be difficult. If all the wells were commingled, that becomes very difficult. I showed you yesterday why the shut-in pressure, it reflects the one layer only. You don't have both layers of average pressure.
But what about that factor? Because I assume usually we are producing different how to say, composition from every well, and then we have a different Z factor for each well.
So if we have a reservoir flow unit, then you would be producing from all of these 5 wells here more or less the same CGR. If you don't have more or less the same CGR, it's probably not the same reservoir flow unit.
Even though if you have a huge reservoir and you have a territorial change of your EVT.
Okay, so if you make this system complicated enough, which is what you're trying to do, I think, or what you're doing, I mean, life is complicated. At some point, you have to abandon using the material balance. In-bow, you have to do reservoir simulation. You have to have 3-dimensional spatial variations of composition. You have to treat the reservoir flow units. You can no longer do simple material balance. At some point, if it's too complicated, you have to give it up.
Okay.
That's the bottom line, yeah. And that's what Dake was trying to argue in this luncheon. The death of the material balance. Life is too complicated. You can't use something this simple, which, of course, I had a heart attack almost on behalf of Mike Fetkovich, okay? Because, Mike Fetkovich, what he said is that you look at the performance of P over Z versus Q, and the non-ideal, the not straight line performance is telling you what's non-ideal if you're clever. And what Dake was saying, just throw it out because it never works.
It's a diagnostic.
It's a diagnostic, the shape of the not straight line behavior. Anyway, they both passed, so they're not going to. Maybe they're fighting now somewhere else, but yeah. Sometimes you just have to give up using it.
We have there is a largest gas field in Pakistan, and so when I was working there, we were the operating company, and if you look at this P over Z plot for that field, it's like a classical straight line, and they are still using it to calculate the in-place number. So you can find the exceptions, but for that field, it worked very well.
Yeah, so there are definitely cases where it's can be used, should be used, and is being used.
It's much easier to try this, see that it's non-ideal, and then do the reservoir complex, model.
Yeah.
And then instead of doing the complex model and then finding that you could have used the easy equation or the easy model.
Yeah. So it's anyway, this is we've kind of used up this session on this topic, but I think it's something that can be done right, can be used, can be useful sometimes, and so okay, so that's